Hello everyone, my name is Jimmy and I'm currently in 10th grade. So I'm just a normal student who's very enthusiastic about physics. So I'm gonna begin a little, I won't call it course, it's just something that I hope that you guys can learn about analytical mechanics. So this is the this is my first time that I posted my video on YouTube, and it's also my first time doing a course kind of thing. So I apologize first if I make any mistakes, and I hope you can learn something from my videos. So first, I'm gonna talk a little bit about analytical mechanics, and I'm gonna compare it with Newtonian mechanics. It's also called classical mechanics, and I think the core of Newtonian mechanics is about vectors. So why do I say that? So let's have an example here. There's an object here, so it's moving like this. It's a rough ground, so it will get. So if we analyze the motion of the object, we do this, like the gravity, the friction, and yeah, this sort of things, and we we do this calculations based on these arrows. This is called vectors, and we pay attention to both its length and its direction. So if if we have an object, however, there are many forces that are exerted on it, like, and the angles are also very complicated. Like this, I'm just giving an example. So it will be very difficult to determine its mechanical state. So that's why analytical mechanics comes out. It's the kind of mechanics that uses the temper with equations in which there are momentums and energy and potential energy and so on. Yeah. So and it's more elegant in many ways than Newtonian mechanics, and we will see later in our series. And also, when things get more complicated, like if we move to quantum mechanics, Newtonian mechanics sometimes it doesn't work for them. So and while analytical mechanics will work just right. So I'm gonna introduce the first several concepts to you about analytical mechanics. So the first concept is generalized coordinates. I'm gonna compare it with Cartesian coordinates. What is Cartesian coordinates? So I'm giving an example, like three axes x, y, and z. They are all orthogonal to each other. So that is Cartesian coordinates. So it's the most basic form of coordinates. So it's very mostly used in Newtonian mechanics. So however, as we move on to analytical mechanics, we tend to use generalized coordinates. By this term, I mean that the choice of coordinates are quite random. So if you can describe the mechanical state of the object in the most elegant way, then you can use it. I'll just give another example. So if we use equations to describe the motion of a pendulum, so it's like a rope, and here we want to describe the motion of this ball here, and we can use the coordinates of like this angle here and the length of the rope here. So use L and theta to describe the motion of the ball, and that will be sufficient. So it's more elegant than we put it into a Cartesian using Cartesian coordinates. So that's what I mean. So sometimes we need more than one generalized coordinates to describe the position of the object. So if we use 1, 2, 3, 4, 5 till s, there will be s generalized coordinates that will be used to define the position in space, and we call the number s as a degree of freedom. I'm gonna repeat it. It's a number that we need to determine the position of an object. We all know that taking the derivative of coordinates, we will get velocity, and it's the same in Cartesian coordinates. Like if the velocity along the x-axis is vx, It is Vx, and it is equal to the derivative of these coordinates in x-axis. Okay. By the way, if I put a dot on x, it means that we're taking the derivative of x, and if I write this, I'm taking the derivative 2 times. We also write it like this. Oh, derivative over time. Yeah. So yeah, that will be generalized coordinates and generalized velocity. Yeah, and degree of freedom. So it's just the basic concepts, and we'll move on to another very basic and important principle. It's called the principle of least action. Well, the proof is quite complicated, and I'm not gonna mention it in this video. However, it's very important. It's like kind of discovery. So the principle states that if we have a function here about x meaning its coordinates, generalized coordinates, and x dot meaning generalized velocity. If we need these two elements to determine the mechanical states of an object, and we put it into the function, the function is about these two things. So we get the concept of the action S. The action is defined as the following here. So it's the function f from t1 to t2, and we calculate the integral from t1 to t2. And the principle states that the increment of s will always be 0. So it's quite abstract. First, I'm gonna put it in an example, so maybe you can know it more, understand it. So here, this is a ball, and we release it from certain height. So from Newtonian mechanics, we can easily get this equation, because like the second principle, F equals to m times the mass times acceleration. So well, a is equal to taking 2 times derivative of the coordinates x. So yeah, we define this as the x-axis, by the way. So we will get this equation really fast. And then after simple calculations, we'll get the trajectory equation for the object. Oh, sorry. So it's here. X equals to half of g times t squared. Yeah, I think that's quite easy to get. So if we draw the graph of this equation, we will get here a parabola, obviously, from t1 to t2. The path, also the trajectory, is this line. So the scientists began to question, if we determine the starting point and the end point of an object, why don't it follow another path like this? In other words, the question will be, what's special about this curve? So why does it follow like this? So after several the efforts of scientists, of physicists, they discover that this equation is the feature of the feature of the path. So here it's just like a very important basic principle of analytical mechanics. So it's not something that can be easily proved. It's something that we discovered. Also, if you're interested in it, light travels in a path that takes the least time. So it's also one part of the principle of the least action. So if you're interested, you can also take search on that. So after we get the equation here, we're gonna do something to it, and we get an arbitrary we get a function here to describe the mechanical states of an object. So if we want to calculate, if we want to get the expression for delta s, we need to get the expression for delta f first. So since f is related to both the coordinate x and the generalized velocity, so delta f can be written as this, and we will write this term into following this equation into this, And here, in order to be easier to integrate, we rewrite this term. We rewrite this term as this, because taking the total derivative of this term is equal to because it's the product of the two expressions. And in order to get this term, we minus this term. Yeah. So here, if we after we have successfully got this expression here about delta f, we put it back into delta s and putting it into an integral. And yeah, there's nothing much here. The integral has linear property, so we rewrite it like this. So this term here is obviously equal to this, because first of all we take the derivative of this term and then we put it into an integral, so it's just equal to this. And the first one we've just keep it here, so it's still like this. However, if we take a closer look at the next term, since we have already fixed our starting point and end point, so the delta x, I'm going to draw it for you. So this is delta x. So delta x is always equal to 0, no matter it's t1 or t2. Delta x, t1, t2, it or equals to, it both equal to 0. And from the principle of least action, the increment of s is equal to 0. So this term is equal to 0. So, and also this whole thing is equal to 0. So this term the first term here must equal to 0. So delta x varies in the graph, it varies. They're different, taking different values of delta x. So this term, the first term, is the coefficient of delta x, this term must equal to 0. So it's this, we get this. So this equation is called the Lagrange equation. So if we take a closer look at it, from this equation we can determine the trajectory of the object, because it's got only f and its component x and the derivative of x here. So it's basically the same form as this trajectory equation is here. So what this means is that if we have already knew this function, specific function that describes the mechanical states of an object, we can know its trajectory by following all these steps and using this important equation. So I kind of simplified the process of the proof to you guys. So here I'm gonna introduce a technically strict proof. If you guys understand, that will be the best. So the function that I talked about, which is related to this function here, that tells the mechanical state of an object, it's actually called a Lagrange function. So it's not only related to q, the generalized coordinate, and the generalized velocity, but also time. However, just as we calculate the increment of s and f, we didn't consider time. So that's where we introduced a new calculation symbol that is called small delta. So this delta means it's like the same as this small delta is actually very similar to the big delta. So what the little delta is to differ from the big delta is that it doesn't consider the derivative, the change of time. So in other words, when we calculate the increment of delta f here, we write it into we write it into sigma f, delta f. We don't have to consider if x is also related to time, but when it's related to time, we need to use this. I'm gonna just emphasize it. It's when the function is related to the time, we need to use this, because we want to ignore the change of time to the increment of the function. So after we write this, we can still write, we change all the big delta to small delta. Oh no, sorry, I made a mistake. Yeah, it will be like this. We ignore this term because when it comes to variation method, this term is ignored. We don't consider this. We don't consider the variation of time. We just consider the variation of other elements, x and x dot. So that's what I mean. And actually the others are the same, and the last we can still get this Lagrange's equation. Yeah, we don't consider the change of time. So this is a special method that we use. It's called the variation method. So next I'm gonna talk about one special property about Lagrange's function. So it's not unique, meaning that even if we have two different Lagrange's function, we can still get the same result and the same trajectory. So we have two Lagrange's function here. So L and another L is different from this one, because L plus the total derivative of an arbitrary function f which is related to Q, generalized coordinates, and time. So this one is arbitrary. As long as the function is related to Q and T, it just can be here. So this two Lagrange's function has a difference of a total derivative of an arbitrary function related to Q and T. So if we put this into Lagrange's equation back here, so here are the calculation process. I hope you guys can understand. So after a series of calculation, we can get here. So if we check on this and the form of Lagrange's function equation here, we can find that this, if we put this into this equation, they have the same. They are the same, meaning that this term has no contribution to the increment of the value, meaning the increment will be 0 even if there's a difference of this term. So as long as the two Lagrange's function has a difference of this, the trajectory of the object is still the same. So that's basically what this property is all about. And here are the calculations. If you guys understand, that would be the best. Yeah, so that will be all the content for my first video, and it's still about basic concepts and some fundamentals about analytical mechanics. So I hope you guys can learn something from my video. Thank you very much for watching.